Alrighty, I think it's time to get started. Welcome back. So I have at least started to post our first homework assignment. It is at the class website, which I had us look at on day one. I'm going to put the link to that in the chat again, just so you have it. You should take a look at there. Every weekend, you know, the homework is always due on Wednesday. I will post it sometime on Friday. Once we see sort of how far we got that week. So I posted parts of it. Depending on how much we do today, I'm gonna, add some more. But that's where you will find the assignment, and you can, submit your answers on Gradescope. It's due on Wednesday. Doesn't have to be before class, just sometime on Wednesday before midnight. Thank you for doing the Gradescope dummy assignment. I enjoyed reading your interesting facts about yourself. Does anybody have any questions about the homework assignment, how it works and all that? I think it's pretty straightforward. Yeah, go ahead.
Looking at it right now, it says more to come on the bottom. Does that mean you're going to add more problems by the end of the day?
Yeah, that's right. Just depending on how far we get today. Yeah.
Awesome. Thank you. Appreciate it.
Yep.
And just want to apologize. My grammar was terrible in my dummy assignment.
Oh, okay. That's fine.
So badly. I apologize.
This is not a grammar class, so I'm okay with that.
I appreciate that, Professor.
All right. Okay, let's talk some more use substitution. We had just a couple more examples at the very end last time, and then we'll go on to something new and different today. So I thought just for warm up, this was not the example we were doing at the end last time. This is just a little warm up to make sure we are still hip to the use substitution early in the morning. So for this one, this is sort of like a standard one. This is not one which requires any extra special tricks. You're going to choose the u to be the inside of the parentheses, which is 1 minus x cubed. Then the du is, someone want to shout it out?
X squared to the negative x squared to the third to the second.
Negative 3x squared. I think that's what you meant. Or I didn't see you said that.
Yes, totally. I'm sorry. It's early still.
Yes, it's a little early to be doing the use substitutions, but that's all right. I've been doing them all night long, right? I'm just getting in. Okay, that's the du. Now, in preparation for plugging everything in, I'm going to divide this negative 3 over to the other side, because that's usually what you have to do. Negative 1/3 du equals x squared times dx. All right? And now I'm going to start doing the substitutions. So this thing becomes integral. Now I see x squared on the top. That's going to end up being part of the du, right? And then what's on the bottom is u to the 4. So I'll just leave this like it is for now. X squared over u to the 4. And then I got dx here. But I want to replace the x squared and the dx. They are this, right? Negative 1/3 du. So as a little, just to make this abundantly clear, a little preliminary step here. I have 1 over u to the 4 times x squared dx, and then that x squared dx is negative 1/3 du. And would you mind if I write u to the minus 4 there? Negative 1/3 du, like that. I wrote it as a negative exponent because that's how you're going to have to write it in order to do the integral eventually. Next step, pull that constant out. Negative 1/3 integral u to the minus 4 du. And then finally I can actually do the antiderivative. So this becomes negative 1/3. U to the minus 4, I increase the power by 1. I get u to the minus 3. And then divide by the new exponent, 1 over minus 3. U to the minus 3. And here I put the plus c because I just did the integral. Everybody good so far? And then one last step at the very end. What do we do at the end?
Substitute in the u.
Yeah, put in whatever the u was in terms of x. Just plug that back in. This is always easy to do. No tricks necessary. Let's combine the constants in front there. I think it's just 1/9, and then I get 1 minus x cubed to the minus 3 plus c. And you can write it in a denominator if you want to. If you don't like the negative exponent, I'll leave it like that. All right. Any questions about that one? This is more or less a straightforward one where you stick the u in and then the rest of it just kind of magically matches up with the du part. All right. Now, the harder one, which we were talking about at the end last time, let's try to revisit that. The harder ones are ones in which you stick the u in, but then the leftover stuff does not exactly match with the du, and you have to play some extra games with it. So the one we were looking at the very end last time was this, x cubed times x squared plus 1 to the power 10 dx. And we began by making the substitution the thing on the inside of the parentheses. And actually, this is the correct u to choose. So you should choose u equals x squared plus 1, and then du is 2x dx. And as usual, I'm going to divide the constant. 1/2 du equals x dx. And I think maybe this was around where we sort of stopped last time. This, you can begin the substitution like I usually do. I'll just stick the u in where it goes. X cubed and then u to the 10 dx, which I'll put the u stuff first just to gather together all of the leftover stuff. And now I think this is exactly where we ended up last time. Anybody been thinking about this one ever since? Had any brilliant ideas over the past 2 days? The problem is really this. X cubed dx does not match x dx. Here's a hint. We could, of course, x cubed, you might say part of this matches x dx. Like x cubed is really x times x squared. So you could split this apart as this, x squared times x dx. All right, this is a weird thing to do, but I mean, I hope you can see where I'm coming from. Where I'm coming from is this doesn't match x dx, and I want it to match, so let's just sort of make it match. All right, I have x dx now, which I can substitute 1/2 to u. Then what am I going to do with x squared? Anybody have a suggestion about what can I do with x squared? You got to look up here. Do you see a x squared anywhere?
There's one hiding in your u.
Yeah, the x squared is part of u, and in fact, you can solve this u for x squared. So this is the other part of the trick here. This u, instead of u equals x squared plus 1, I can write x squared equals u minus 1 and plug that in down there. So where you see x squared down here, I'm going to plug u minus 1, and where you see x dx, just in the usual way, I'm going to put 1/2 to u. So what do we got? U to the 10, x squared is u minus 1, x dx is 1/2 du. Right? This is the trick. Now everything is in terms of u's, and hopefully we can do this antiderivative. Any questions about that? Any thoughts? You got to be slightly creative, I guess. Although I think once you've seen this trick done a couple times, it's not so hard to realize when you see something weird which doesn't quite match. Maybe try to pull out a piece of it which does match, and then take a look at what's left over, and hopefully that can match part of the u. That's the basic idea. What do you think about the integral? What should we do in order to finish off here? That we've done sort of the hard part was that substitution. What do you think about finishing up?
Now we just have to integrate it.
Yes, we have to integrate it.
I can do the first part of that if you'd like.
Sure.
We're going to end up with 1/11 u to the 11th times 1/2 u squared minus 1.
So actually there's something you got to do before all of that. Right here we have a multiplication, u to the 10 times u to the minus 1, and you cannot just do integrals of each part of the multiplication, unfortunately. How do we get around that?
Distribute it.
Yeah, you got to distribute it. Thank you. So, and I'm also going to pull this constant out, if you don't mind, 1/2 on the inside of the integral. I'm always going to take those constants out. Oops. So 1/2 here, integral sign, and then inside I'm going to distribute. So I go u to the 10, distribute like this, right? I get u to the 11 minus u to the 10. du. And now from here, we can do the antiderivative of each of those things. 1/2 out front, and then it's going to be 1/12 u to the 12 minus 1 over 11 u to the 11 plus c. And finally, the very last step, you plug the x's back in. So remember u, way at the beginning, u is equal to x squared plus 1. And so down here, these u's become x squared plus 1's. 1/12 x squared plus 1 to the 12 minus 1/11 x squared plus 1 to the 11. All right. That's how we do it. This is a, I would say, sort of advanced kind of u substitution. Not obvious how to make it work out, but you can do it. Any questions about all that? It's a tricky one. Sometimes I like to be tricky. Okay, I think that's all we got to say about the u substitution then. I want to move on to the next section. That was, if you're following along in the book, that was section 4.5. I don't know if anybody cares. And then the next section is in the next chapter, chapter 5. Although it's really sort of more of the same stuff. It seems an arbitrary division between 4 and 5. But chapter 5 is all about more things that you can do using the integral. So everybody knows the integral can be used to find the area under the curve. And the integral also can be used in certain real-world problems which are about rates of change, kind of the inverse to that, the total change over a certain duration of time. But anyway, there are yet more things that you can do with the integral, and section 5.1 is all about what they call area between curves. All right? If you have one function, you can use the integral to find the area between that function and the x-axis. But this section is all about, what if you have two functions? Let's say I got my f here and a g that looks like that maybe. And I want to know what's the area between these two functions over a certain range from a to b, say. This area here. This is what is meant by the area between the curves. All right? Once you know how to do it, actually this is typically not very difficult to do. There's a very simple, I suppose, formula to remember, although it's not even, it's so simple that you won't even really have to think of it in terms of memorizing a formula. But can we just think first of all about how would you find this area if you didn't know anything? This traditional approach in any sort of thing involving the integral even vaguely is to chop up the domain into a bunch of little bits, right? Now I hope you remember doing some examples with this. You probably learned about, do the bits with the left endpoints or with the right endpoints or with the midpoints, or maybe you did like the Simpsons rule, the trapezoid rule. We're not going to get into all the details of that, but I hope that you remember like those things do exist. And the basic idea behind them all is to chop up this region into a lot of little bits. And the bits I'm going to call, in our book, they call them x0, x1, x2, x3. These are the little sort of subdivision points. And you cut them up in such a way that the width of each one is called delta x. But anyway, you would make little rectangles on here. And the rectangles sort of match up with the shape you're trying to look at. They maybe they don't match up exactly, but they match up vaguely with the shape that you're looking at. All right, and then we add these rectangles. So the area between the curves is approximately equal to the sum of the rectangles, and I said approximately because the rectangles don't exactly match up the curve because the curve is curvy. It's not actually made up of rectangles. But the idea is you make the delta x super small so that when you do this rectangle thing, what you would get if you added up the area of the rectangles is very close to the true area of the curved region. All right. What I want to talk about is what exactly is the area of each rectangle. So each rectangle looks like this. I'm going to kind of blow it up a little. where this is, say, xi, some one of those points, and then this is like the next one, xi plus 1. But that's not so important. This distance is delta x. So the area here of this one is, it's the base times the height. The base is delta x times. And how could we find the height of this rectangle? That's really the important thing to discuss. In terms of our original functions, can you tell me what the height would be?
Wouldn't it be f of x minus g of x at a specific point?
Yeah, right. So, I mean, this would depend if you're using the left endpoints or the right endpoints, but let's imagine we're using the left endpoints. Then the height of this rectangle is determined by those 2 points on the left side, and it would be the top one minus the bottom one. So I'm going to say it's like f of xi minus g of xi, right? Where I put the f first because the f is bigger. Now, if you had some example where the g happened to be smaller, then you would do the g minus the f. But anyway, if we are going by the picture that I drew up there, the f was above the g, and so you subtract them in this way. All right? And so the total area between the curves should be what you get if you add up all of those things. So the total area between the curves is approximately equal to the sum of delta x times f of xi minus g of xi, where the sum goes something like, I equals 0 to n, if you like, where the I equals 0 would be the leftmost endpoint, x sub 0 is the leftmost endpoint, and xn is the rightmost endpoint. But anyway, what happens, really the true area is this, but with delta x approaching 0 in the limit. And what do you get when you have this kind of sum? Is called a Riemann sum. I hope you remember that word. Some people say Riemann. I've heard some people say Riemann. It's not. It's Riemann was his name. He's not a rapper or something. Riemann sum. Anyway, the what do you get when you take the limit as delta x goes to 0 of a Riemann sum? You get the integral of that function that you see inside there. So when you take the limit here, so the true area is this, but with the delta x going to 0, I will say, i.e., the true area actually equals the integral from a to b, because those are my 2 endpoints, of the function f of x minus g of x dx. So the delta x, sort of, this is a little informal magic here, but this is how Riemann sums work. When you take the limit of a Riemann sum, the delta x kind of becomes the dx, you imagine, and then this thing here, the function with the various individual points plugged in, it becomes the integral of the function, not with specific points, but just the function with, you're sort of like plugging all the points in, but of course you're not. You don't actually do it that way, but that's what the integral is. All right, this is the formula to memorize. So for f of x greater than g of x, the area between the curves is the integral a to b f of x minus g of x dx. All right. Can you remember that formula? It's not much of a formula at all. It's the bigger one minus the smaller one. That's all you got to do. All right? Biggie minus Smalls, as they say. Remember that guy? Rest in peace, Biggie. All right? Let's try a simple example, and then we'll do some, less simple examples. The basic idea, I think, is very simple, but let's just try some. How about let's find the area between x and x squared, where they cross. So what I mean by that is if you draw the graph of these things, you will see, everybody knows y equals x looks like that, and y equals x squared looks like that, And there's this sort of overlappy region here. That's what I'm talking about. The area between those two curves, where they cross. What I mean by that is that red space there, right? The area between the two curves. This is almost a very straightforward, you know, plug into the formula in the box there. The only extra little bit of work that you need to do here is to figure out where are the A and the B, right? In this case, I drew the picture for you, but I didn't actually tell you where those points are. Now, if you know even a little bit about these functions, you know the point on the left is 0. That's where I drew it. And the point on the right, where's the point on the right?
It has to be 1, right?
Yeah, it should be 1, right? If you think about what are the numbers for which x is the same as x squared, they are 0 and 1. Now, if you didn't want to do that in your head, we can find the intersection points. In this example, you can just kind of guess it, but in a more complicated example, we would find the intersections by setting the two equations equal to each other, right? That's how you find where two graphs of two functions meet. Setting the two equations equal to each other. So in this example, we get x equal x squared, and then we have to solve this for x. This is like a quadratic, so I would put everything on the same side. X squared minus x equals 0, and then factor. And then this says x equals 0, x equal 1 are my two solutions. All right, so I figured it out by the equations, although in this example you probably could have figured that out just kind of by common sense, but in a more complicated example, this is the procedure you would do. Anyway, now we can, you know, set up the integral sign and do it, right? This is the formula in the box. From a to b, f of x minus g of x. So I go integral a to b. In this case, the a and the b are 0 and 1. And then I want f of x minus g of x. Which way around should I do it? It's, you know, the two functions are x squared and x. You're either going to do x squared minus x, or you're going to do x minus x squared. What do you think? Maybe I will call on Daniel. Do you go by Dan? Daniel?
Either one's fine.
All right. What's it going to be? X squared minus x, or are you going to do x minus x squared?
I'm going to go with x squared minus x.
You want the bigger one minus the smaller one.
Yes.
Yes. In ordinary conventional wisdom says that x squared is bigger than x. Although, if you do you believe my picture here?
Yeah, it looks right.
So you may want to reconsider which one is bigger on this region here.
Oh, the x.
Yeah, I think x. So usually it's not. Usually x squared is bigger than x, but in this case, since we're considering the values between 0 and 1, actually in this case the x is bigger. So I go x minus x squared. Great.
Had a 50-50 shot.
Yeah, right. It's because for these particular values, x is bigger than x squared. Usually it's not, but here it is. All right, and now this is an easy integral to do, right? We might as well finish it off. I'm going to go 1/2 x squared minus 1/3 x cubed, plugging in 0 and 1, and you plug them in. You get, when I plug in 1, I get 1/2 minus 1/3, and then when I plug in 0, I get 0 and 0. So this is just a half minus a third, which is 1/6. All right, because I'm a fractions master. Any thoughts about that one? Questions? That's the area of that little red guy.
Where did the 1/2 and the 1/3 come from?
Yeah, they come when I do the antiderivatives. So x squared, I increase the 2 to a 3, and then I put the 1/3. Is that what you meant, or did you mean these ones?
But no, I meant for that one, and then the exponent for the first x. What is the exponent for that?
Yeah, so when you see just x, that means x to the 1. And so then I increase, this is a x to the 1, I increase it to a 2. Is it just hard to read? Yeah, it's not a very good 2 there. Yeah, increase it to a 2 and then divide by the 2 up front. Yeah. Great. All right, so that's a fairly straightforward one. Let's try another one. It is a little more interesting when the two curves have some crossings. So let's try a new one. Find the shaded area. How about this? I got two functions which are just lines. This one is y equals 2x plus 1, and this one is y equals minus x. And I would like the area when you go over to 2 and back to minus 3 here. And I want this shaded area. Right? The butterfly. Or it looks kind of like a bat. Here's a pro parenting story. You want to hear my parenting story of the day? I used to, my kids are like 10 and they're 11 and 13 now, but when they were littler, you know, you make the kid the sandwich, right? And then I would say, you know, you can cut it this way, right? No kid wants the sandwich cut down the middle like that. No. My girls, they wanted butterflies, so I cut it this way, and then rearrange them so that they're like this. That's what this reminded me of. You get the butterfly sandwich, all right? Isn't that great? Or you can cut it, here's an extra tip. You cut it that way, then you get two little butterflies. Isn't that great? And around Halloween, I would say, you want butterflies or bats? And they would say, oh yeah, we want bats. Here's the tip. The bat is the same as the butterfly. You just say it's a bat. They went for it. Yep. That's this picture reminded me of that. The butterfly or the bat. Don't matter. So this point here is 2, and this point back here is -3. So in this one, it's not such a big deal to find the two boundaries in the integral sign, right? Last time we had to work out what the 0 and the 1 were. Here I just straight up told you what the two endpoints are. But the problem is there's a crossing in the middle, and the crossing in the middle causes the sort of the biggie and the smalls to reverse roles, right? On the left side of the crossing, one of them's bigger, and on the right side of the crossing, the other one's bigger. That means we actually need to divide this into two parts and do two separate integrals, one for the left piece and one for the right piece. So we got to split this into two integrals, the left side and the right side. And unfortunately, that means we do have to find that intersection point in the middle, because we're going to need to know where that point is so that we can split it up and use the intersection in the middle. So we got to find this value right there in the middle where the two wings meet. And to do that, we do it in the usual way. Sorry, give me a... We do it in the usual way, which is you set the two equations equal to each other. Now, I said it was 2x plus 1 and -x. So the intersection, first of all, we got to find that point. It is, I set the two formulas equal to each other, right? 2x plus 1 equals -x. And we solve for x here. What do you get when you solve for x? -1/3. Yeah, that's what I get. If I add the x to the other side, 3x equal -1, and then x equals -1/3. Okay, so that looks, I don't know if that looks right based on my picture, but it is -1/3. And so I said we're going to split it into two integrals. The two integrals are going to be the integral from -3 to -1/3 of something, and then I add that plus the integral from -1/3 to 2 of something. All right, these are my two integrals. This is what I meant by split it up into two integrals. This one represents the area on the left side, and then this one represents the slightly larger area on the right side. So you find each of those two areas and you add them together. You can't do it as a single integral in this case because the roles of the f and g switch where they cross that intersection point. All right, but each one of these individually shouldn't be so hard to do. So let's start with the one on the left. We go integral -3 to -1/3 And then it's going to be, as always, the big one minus the smaller one. And you have to look on the picture at this particular part of it, the left side. Which one is bigger on the left side? It's the minus x is bigger. So I go minus x minus the other one, 2x plus 1. All right. By looking at the picture, you can tell on the left side, the minus x is bigger, and the other one is smaller. All right. And now we can do this integral like we always do. Let's just simplify this first. You can combine that stuff, right? It's minus 3 to minus a third, and then I got minus x. Let's distribute the minus sign. Minus 2x minus 1, right? And then you can combine those x's. They add together. You get negative 3x minus 1. From minus 3 to minus a third. And then I do my antiderivatives. How about John Flint? Can you tell me the antiderivatives? Are you there? You're the only one I can't see. Oh, there you are.
Just negative 3.
That, I think, is the derivative.
Oh, that would be...
So,
negative 3 over 2x squared.
Yeah, right. Minus, and then what happens to the 1?
Minus x.
Yeah, excellent. Great. Oops. All right, and then we plug the numbers in. Okay, so it's just going to be some bunch of numbers, right? Negative 3 halves, negative a third squared minus negative a third, and then I subtract and plug in minus 3. Negative 3 halves, minus 3 squared minus negative 3. There you go. This is the area of the piece on the left. All right? As usual, I'm just going to leave it like that. If you want to plug it into your calculator, that's fine. All right. Everybody with it so far? This is not my final answer. That's just the piece on the left. Now the piece on the right. All right. The piece on the right is the integral. So this is the one on the left. Now the other piece, integral minus a third to 2. And this time, I again do the bigger one minus the smaller one, but this time it's the other way around. If you look on the picture, you can see in this region, the bigger one is 2x plus 1. And then I subtract the smaller one, which is minus x. So it's like that. And again, we got to do this integral. The two integrals will end up being similar to one another. It's more or less the same function. It's just the opposite, right? When I combine this stuff together, it's just going to be 3x plus 1. It used to be minus 3x minus 1. This will always happen in examples like this. You should get the same function, just the opposite signs on everything, because the whole point of these, what changes from one to the other, is the order in the subtraction changes, which has the effect of introducing or removing a minus sign. Anyway, let's do it. So it's the same idea for the integral. You get, oops, I'm doing the integral. 3 halves x squared plus x, and I plug in 2 and minus a third. So for this part, I get 3 halves times 2 squared plus 2 minus 3 halves times minus a third squared plus minus a third. There you go. This is the other part. This is the area on the right side. And so the total area is those two things added together. Would you mind? This is annoying to write down. And if you want to do this on the homework too, that's fine with me. The total area is, you know, this plus this, right? This plus this. That's my answer. If you had been plugging into your calculator as you went, then it's not so hard to just add the two numbers together. But if you don't want to do it on your calculator, it's those two numbers added together.
So on a quiz or exam, we wouldn't have to simplify any farther than that?
Yeah, that's right. Yep.
Awesome.
And you can even draw the boxes and the arrows if you want. All right. Any other questions about that? Great. Okay. There's a few, you know, the basic procedure doesn't get much harder than that. There's a few variations that you may see on the homework and on our tests or whatever. Here's a little variation. Let's find the area between y equals 1/2 x. So I'll draw the picture here. Y equals 1/2 x is like that. And x equals y squared minus 3. Now you can see what the variation is. This one is not a function in the traditional sense, or it is a function of x in terms of y. But anyway, y squared minus 3, that looks like a parabola but sideways, right? When you see y's in terms of x, it's the same idea, but everything is sideways. Y squared minus 3 will be like a parabola but going this way. All right? And I want the area between these two things where they overlap. So there is another intersection point over here, and not there, an intersection point down there, right? And I want this area. That area between the two curves. So what is tricky about this? I mean, obviously it has to do with the fact that one of those is not a function. And the real issue that this causes is, if you think about it in terms of like doing the sort of the Riemann sums, we're not going to use the Riemann sums, but the whole idea of this is based on Riemann sums that go like this. Now, in this, for these rectangles that I'm drawing right now, there's not really a problem. You have the height of the rectangle is given by the difference between those two functions. So this is not really a big issue. The issue comes over here, though. If you continue drawing these rectangles all the way across, you will notice these rectangles are different. The height of this rectangle is not given by the difference of the two functions, because this is actually the same function both times, right? Both sort of edges of the rectangle are determined by the same function. And that means our usual formula about f of x minus g of x is not going to apply to this one, because the f and the g, you know, sometimes it is given by the difference f minus g, but over here it's not. It's f minus f somehow, but that doesn't make sense because it's not actually 0, right? So what we got to do instead of those, I'm going to erase those boxes. Don't think of it that way. The answer, or the strategy is do the whole thing sideways. Instead of considering this as functions in the usual sense, I'm going to look at them all this way, right? Because then actually, if you draw the rectangles this way, actually does work all the way across the whole figure, right? In that case, it's always like the left one and the right one, all right? And in terms of x values, you want to take the one on the right minus the one on the left, because the x values, the bigger x values, are to the right. So how exactly do we do the whole thing sideways? What I mean technically is write everything as a function of x in terms of y, not y in terms of x. So write everything as a function of y, and in particular what I mean is solve for x in both equations. Now, one of the equations is already solved for x, so you don't have to work too hard for that. It is x equals y squared minus 3. The other one, I want to solve for x, and we can do that pretty easily. This, y equals 1/2 x. Of course, if I solve for x, it'll say x equals 2y. So, like that. And now we just do everything the same way as we always did. So, I will just say then do integral something something. You got to find the two endpoints, but then I want big E minus smalls as usual, but this time it'll be dy, right? Everything in terms of y, not x, because we're doing it all sideways in terms of y, but not x. All right. And in this case, big E, like which one is bigger, means the rightmost, right? for ordinary functions, the bigger one is the one that's further up. For functions of x, the bigger one is further to the right. That's because that's where the positive x values are. They are further to the right than the ones to the left. So the bigger one is the rightmost, the smaller one is the leftmost. All right, this is the idea. I think we got all the ingredients here. Maybe not quite, actually. We have our two functions. What we should begin with is the two endpoints. You have them on the picture, but I didn't tell you exactly where those two endpoints are. And these, let me just emphasize, these are y values of the endpoints, right? Because I am doing the entire problem in terms of y's, not x's. So what you want to put there are the y values of those 2 points that you see marked on the graph. Right? How can we find those 2 points?
You just set the equations equal to each other.
Yeah, set the equations equal to each other, and you want to set them equal so that you keep the y's, don't keep the x's, because I want to eventually solve for y. So to find the endpoints, I set these 2 formulas equal to one another. That is y squared minus 3 equals 2y, right? And then we solve this for y. This being a quadratic, I'm going to put everything on one side. Y squared minus 2y minus 3 equals 0. And now you can solve this. You could use the quadratic formula if you're an insane person, or you could factor. What do you think? Anybody, any factoring master there? What do you get?
It's negative 3 and 1.
Yeah, so this becomes y minus 3 and y plus 1. And so my solutions are y equals 3, y equals minus 1. And just as a sort of sanity check, that does look reasonable on the picture, right? That means this point here is y equal minus 1, and this point here is y equal 3. Oops, 3, right? And that seems reasonable, given the picture there. Okay, so let's set up the integral then. Our integral will be integral from, all right, I go minus 1 to 3. Those are the y values of the 2 endpoints. And then inside I have my functions. It's going to be the big one minus the small one, which in this case means the one on the right minus the one on the left. So what does the formula inside the integral sign look like? What do you say, John Kroger?
Isn't it just a large function minus the small one?
That's right. Yeah, so what's it going to be?
So it's y squared minus 3 minus 2y.
So in this case, you want the bigger one. In terms of x, the bigger one is the one to the right, and the smaller one is the one to the left. So I think on the picture over here, the bigger one is this one. This is bigger. In terms of x values, it is.
Oh, okay, so 2x is the bigger one.
Right.
2y.
So I want 2y,
I was
right.
confused by the model. I didn't know which one you're talking about.
Yeah, it's a little confusing. 2y minus, and then the smaller one is the other one, y squared minus 3, like that. And it's going to be dy. Great. From here, it's just ordinary, doing the integral. So we get minus 1 to 3. Let's just distribute the minus sign in there. Like that. 2y minus y squared plus 3 dy. And then I integrate. It's going to be y squared minus 1/3 y cubed plus 3y. And evaluating at 3 and minus 1. And then plug them in. All right. 3 squared minus 1/3 times 3 cubed plus 3 times 3 minus negative 1 squared minus 1/3 negative 1 cubed plus 3 times negative 1. Like that. That's how we do it. This is the area of that region Any questions about that one? Same basic idea, but everything is in terms of y, which makes it a little confusing, I guess. All right. Great. I got one more example of the area between curves thing, and then I think we can go on to the next section. Today's our long meeting, right? One more example. So the last thing that might make this a little harder. So one thing which we're not going to talk about, but it can happen that there's more than one intersection point, in which case you have to break up the integral into more than 2 pieces. You might have to do 3 pieces. That can happen. It's not a big deal. Here's one that I want to try. How about what if we can't see the graph? This will make it slightly harder. So what is helpful about seeing the graph? First of all, you can sometimes see what the endpoints are on the graph, and also you can see which one is bigger and which one is smaller. If you can't see the graph, you have to figure all of that out by hand. So let's try one like that. How about find the area between y equal x squared minus 4x and y equal 2x. So these are both ordinary functions. And I'm going to say between x equal minus 2 and x equals 2. All right. What we have here is a line and a parabola. I told you the endpoints, but we don't know if the curves cross each other or not inside that region. So if they don't cross each other, then you can just do a single integral. But if they do cross each other, then you have to break it up into 2 pieces, right? This is, we saw example like that, like the butterfly or the bats, right? That one, they crossed each other, so you had to break it up. We don't know if they cross each other or not. Could we determine if they cross each other? Yeah, we should look for intersections. Now, maybe there isn't one, but we need to check to see if there is or is not. So I'm going to say we got to check for intersections. And in particular, actually, we only care if they're intersections between minus 2 and 2, right? Because that's the region that we are trying to find the area on. If there's some intersection outside of that, then it doesn't matter to us. It's only if there are intersections between those values that really matters. Okay, let's do it. The way we do it to check for intersections, as always, is to set the 2 formulas equal to each other. So I'm going to go x squared minus 4x equals 2x. And I solve in the usual way by putting it all on one side. X squared minus 6x equals 0, and then factor. So I get x equals 0, x equals 6. So actually there are 2 intersections, which is not a surprise. If you have think about a parabola and a line, you would expect either 0 intersections or 2 intersections. Although one is possible. One of these intersections we don't care about, right? This x equals 6 is irrelevant. It's not wrong, but it just doesn't matter for our purposes because we only care about the region between -2 and 2. And so x equals 0 is important. So we are going to need to split this up. We'll split it up. One of them will go -2 to 0 of something, and then the other one will go 0 to 2 of something, right? Because I have these 2 curves, they are crossing each other at x equals 0. And so we need to do the stuff to the left of x equals 0 and also the stuff to the right of x equals 0. They cross again at 6, but that doesn't matter. All right. There's one more thing we need to determine. So for this one, -2 to 0, we have to find out which is bigger. Is it x squared minus 4x or is it 2x? Right? In order to set up the integral to actually find the answer, you got to do the bigger one minus the smaller one. And if you don't have the picture to look at, you don't know which is the bigger one versus the smaller one. Anyone want to suggest how we could figure that out? There's kind of an easy way and a hard way.
Could you just plug x values for your range?
Yeah, maybe just choose your favorite x value in this range between 0 and -2, and just see which one is bigger. This, I would say, is the easy way. Don't choose 0 because they're equal at 0. That's the point of that. But we could choose any other point. So let's choose some point between -2 and 0. Plug into both, and that will tell you which one is bigger, right? So let's choose. What's your favorite number between -2 and 0?
-1.
-1. It better be. Yeah, since you're going to plug this number in, there's no reason to choose a more complicated number. You want to choose sort of your favorite, easiest number to plug stuff into. So I'm going to pick x = -1. And what do we get? So x squared minus 4x, when I plug in x = -1, I get -1 squared minus 4 times -1. And this, you actually do have to work out what this number is, because you intend to compare this to the other number that I'm going to get. So this one, unfortunately, you've got to do the arithmetic here. But I hope you can handle 1 plus 4 is 5. All right, and then the other one, 2x. Okay, when I plug in there, I get 2 times -1, which is -2. So in this region, so on -2, can I just write this interval? On -2 to 0, x squared minus 4x is bigger, right? And the other one is smaller. And so this piece is going to be, all of this was just preliminary work to set up the integral. Integral from -2 to 0, bigger minus the smaller. So it's x squared minus 4x minus 2x. That business about plugging the points in was just so that we could figure out which one was bigger, so that we know which way to subtract them. Bigger minus the smaller. All right, what's that going to be? Simplify inside first. It's x squared minus 6x dx, and then we do the integral. 1/3 x cubed minus 6 over 2x squared. 6 over 2 is 3, of course, but whatever. Plug the 0 in, I get 0 minus 0, and then subtract, plug in -2. 1/3 -2 cubed minus, I'll write a 3 there, -2 squared. All right, this is the first area. We're getting there eventually. There's a lot of steps, but I hope you feel that each individual step is not really that hard. It's just you gotta put together a lot of ingredients. Okay, so all of that was the first part, the integral from -2 to 0. Let's also check. So now I want to do the integral 0 to 2. All right. We again need to determine which function is bigger. Now, usually when two functions have an intersection, the one which was bigger on the left side becomes smaller, and the one which is smaller becomes bigger. Although that's not always going to happen. It is possible to have two curves that intersect, but they don't cross each other really. They could have some intersection like that, where they meet, but they don't actually cross over. And so it is necessary to check both times which is bigger. Again, we do this by plugging in. What's your favorite number between 0 and 2? The answer is 1. I'm going to plug in x = 1 to each function, right? The first function was x squared minus 4x. I get 1 squared minus 4 times 1. That's 1 minus 4, which is -3. And the other one was 2x. I get 2 times 1, which is 2. And so in this case, 2x is bigger. All right, and so I can do my integral. Integral 0 to 2, 2x minus, the other one was x squared minus 4x. Make sure you have those parentheses in there, because you're going to have to, when you simplify before doing the integral, Dem's parentheses will make them add together, right? 2x, it's going to be 2x plus 4x, which is 6x minus x squared. And we do the integral. 6x, just like before, becomes 3x squared minus, and then a 1/3 x cubed. And I plug 0 on 2, and I get 3 times 2 squared minus 1/3 times 2 cubed minus a bunch of zeros. And this is my other half of the answer. Any questions about all of them?
Is it always going to be opposite when you split into two, like the functions, which one's on top and which one's on bottom?
Not always. That's what I was trying to explain with this little picture over here. Here's an example where two functions. So yes, most likely they are going to swap their roles, bigger versus smaller. But it can happen that they don't. You should feel like an intersection that looks like this is somehow unlikely to occur. But I mean, who's to say? When I'm inventing the questions, I might just try to mess with you and make it intersect like that. So you got to check it. All right. So I might as well just write my final answer. So come on now. So the total area is the sum of these two things, this and this. That plus that. Right. I think that's all there is to say about the area between curves. Any questions about that? The area between curves, actually, maybe I'll just mention, is actually used in the real world to do certain types of things. There's an interesting thing which they talk about this in the book, and I thought about getting into it, but I didn't want to take up a whole lot of time about this. But there's an interesting thing in the real world called the they call it the Genie Coefficient. This is pronounced Genie. The Genie Coefficient. This is a measure that's used in the real world of economic inequality. You know how people sometimes say, like, our economy is all messed up because, like, the top 1% of the people have 90% of the wealth or something like that. This is the kind of thing that I mean when I say income inequality. That I'll just give you the very short version of this. In an ideal equal economy where there is no economic inequality, I will say ideally, you know, when they say things like the top 1% or whatever, if they say things in terms of bottoms instead, you would say the bottom 99% only has 10% of the wealth or something like that. And this is viewed as improper. It should be that the bottom 99% has 99% of the wealth, or at least you feel like that's the way it should be in an ideal situation. I would say the X% of the population should have X% of the wealth, right? Or the income, if you want to talk about income inequality or whatever. But realistically, it's a lot less than that. The bottom 90% only has, you know, 20% of all the wealth. That's how it works in the real world. You can express this as two sort of lines in terms of percentages. This is like the ideal line where y equals x, meaning the bottom y% of the people have x% of the wealth. But in reality, the bottom y% of the people have actually less than that amount of the wealth. The true curve looks like this, something like this, where eventually when you get to the top 100%, they have 100% of the wealth. But the lower values of this have lesser wealth. So this is like the true distribution is down here, where in a perfectly equal society, it would be all the way up at the line. And so if you want to look at different countries around the world or different economic groups or within one country, different states in the United States or something like that, the way you can measure the income inequality is by measuring the area between these two curves. And this is actually how this is done in the real world. And you can look up, if you look up, look this up on Wikipedia, you can see a big list of like all the countries in the world and their various Genie coefficients, which represents this area. And if that area is 0, that's good, because it means that there is basically no inequality. And now it's never 0. Nowhere in the world is that area 0. If the area, so the worst case that this could possibly be is this area could be 1/2. And that's not even really possible, but that's the theoretical limit of what that area could be, is 1/2. I think the last time I looked at this list, the United States is, people complain about this about the United States, but on a global scale, the United States is not terrible. It's something like around the 30s, where the top of the list is the worst, and that is South Africa has extreme income inequality. United States is around 30 on this list, a list of all countries in the world. So 30, I mean, not so bad. Number 1 is the worst. We're slightly worse than the middle of the pack, I guess. But it's interesting, I think. This area between curves is actually used for things in the real world. That's all I wanted to say. That was my 5-minute version. If you're interested, you could read up on this. There's a big section in the book. I decided to skip over it because we got other stuff to do. Any questions or thoughts about that? I will just mention another way you can try to measure income inequality, which is a different measurement, is by measuring, instead of that area, if you don't like areas, you could just look at these two lines and try to find, maybe it's around here on this picture. There is a point at which there is some greatest vertical distance between the two lines. So instead of looking at the area, you could look at where are the two lines furthest separated, and that has another name. This is called the Hoover Index, which is named after another person. You can also ask every country in the world what's their Hoover Index. It's another way of measuring the same thing. There are many ways of measuring income inequality. These are 2 of them. One is based on the area between curves. All right. Any thoughts about that? No. It's interesting that this is useful for something in the real world, other than just, I mean, sometimes when you take a calculus class, you begin to feel like it's just a bunch of random stuff. Like, if you really wanted to find the area between 2 curves, you could in this way, but who really wants to do that anyway? The fact is, for geometric reasons, not a lot of people really care about. You're not in your ordinary life going to want to do this, but it is actually useful in some more abstract settings. All right, we got about 10 more minutes. I think that's enough time to sort of get a little start on the next section. So that was section 5.1 in the book. Let's talk about section 5.2 is using the integral to find volumes of things. This is something you may have done if you had a fancy calculus class in high school. Volumes of things using the integral. Of course, the integral is used principally for finding areas of things, but if you do some tricks, it's not so hard to use the integral to find the volumes of, at least certain types of shapes are fairly easy to find their volume using integrals. And we are going to focus on solids. They're called solids of revolution. Solids of revolution. What this refers to is solid objects which are formed by revolving something. You got to imagine like something you could make on like a spinning potter's wheel, something which has some sort of rotational symmetry to it. I'm referring to, if you begin with a function, say f of x, looks like that maybe. How about a little more shapely? Here's f of x. And then I want to consider the volume that I get if I revolve that function around the x-axis. So spin the graph around the x-axis. You get a three-dimensional object, and it looks sort of like this. This side gets spun down there, and you get this kind of a cocktail dress kind of thing. Is that what a cocktail dress is? I don't actually know. I'm not experienced.
Kind of.
Kind of? All right. Depends on your body type. Okay, you spin the graph around the x-axis, you get this kind of shape. And the question is, can we find the volume of such a shape? Now, this is like a weird cocktail dress shape, but actually many of the standard shapes that people care about they do have this kind of rotational symmetry, like a sphere does, a cylinder does, a cone does. These are all examples of shapes which you can obtain by spinning around the x-axis in this way. Okay, let's talk about it. How would we find the volume using an integral? Well, if you're going to use the integral, you will not be surprised to hear that the basic strategy is to cut it into slices, right? This is always the approach when we're using the integral to measure something, is by measuring that thing by imagining that you chop it up into a bunch of little bitty bits. And if you actually do the bitty bits, you can add them together like using the left endpoints or whatever. We're not going to do that, but we're going to see how you can use the integral to do this. Now, I'm going to slice it up this way, sort of vertically, which really on the picture sort of looks like that. You get these curvy bands that you are slicing this thing into. All right. Sorry, my picture looks a little messy at this point, but each slice. Oh, and then let me just finish what I was saying. You cut it into slices and then add up all the volumes of those slices, right? The typical approach, you know, using the integral to do the area, you cut it up into a bunch of little chunks, which are typically rectangles, and you add the rectangle areas up. In this case, we are slicing it up into a bunch of shapes, and then we're going to add up the volumes of each of those shapes. Each slice looks like... Could someone describe in words, like if you were to grab one of those slices and pull it out, what kind of a shape is it?
I think it's going to look like one of those pieces of pineapple that you take out of a can of pineapple.
Okay, yeah. Without a hole in the middle, right? I mean, in this particular example, I'm considering that whole thing as being solid. Yeah, it's a it's sort of like this, right? It's a circle. You might say it's a circle, but it has thickness to it, right? Can anybody? There's actually like a mathematical name for that shape. Anybody know? In fact, it's a very common word. Maybe it's not a weird.
A cylinder?
Yeah, it's a cylinder, all right? It's kind of on its side and very thin, but really it is just a cylinder. So, if my goal is to if my goal is to add up the volumes of all of those things, we are going to need to remember the formula for the volume of a cylinder. I don't know if you remember this formula, but I will refresh your memory. So, a cylinder, ordinarily we write this way, which has a certain height and a radius. Those are the two ingredients in the formula. Anybody actually remember this formula for the volume of a cylinder?
1/2 base times height. Is that the one? Or?
That's the area of a triangle.
Wrong shape. My
yeah.
bad.
It's going to involve the radius and the height.
Pi r squared times height.
Yeah, it's pi r squared times the height. This is the cylinder volume is the same as just the area of the circle, like on the top, and then times the height. I don't care if you remember that formula, but now that I say it, I hope you believe me. The volume of each slice is pi r squared times h. All right. So if I make my slices in my usual way, which is to say each of these little points, the x values, my picture is a little messy. I'm going to redraw this picture. This is where I'm slicing, right? And it goes this way. But these are, you know, x0, x1, x2, and the width of those is delta x, as usual. This is how we always write. This is how I'm usually going to write when we do this kind of Riemann sum setup. What is the volume of a slice? So one of those slices is like, looks like this, right? Or if you draw it on its side, it looks like this. It has a very sort of short height to it. So each slice volume is, it's a cylinder, so it's pi r squared h. What is that exactly? Pi, in this picture, in terms of the quantities that I'm writing here, can you say, for instance, what is the h?
Is it just the bigger minus the smaller?
No. The h would be here, right? In the cylinder. Where does that come from in the original picture?
Is it the change in x?
Yeah, that h is really the delta x, right? Because these cylinders, they come from, you know, they lie that way. So the height here is delta x. And then what is the r? The r would be that, right? This distance here, which on the original graph looks like this. So the r actually is given by the value of the function, right? The r is simply f of x. Or for individual points, it's, you know, f of xi or whatever. And then it should be squared like that. So each slice volume is given by pi times the function value squared times delta x. And just like before, we're going to add these all together. So we add them up. We get the sum pi f of xi squared times delta x. And then we can take some kind of limit. So I will say in the limit as delta x goes to 0, we get an integral, right? It becomes the integral from a to b. Now, what's inside the integral is this stuff, right? The delta x becomes dx, but what else becomes this? And this is the formula for the volume of a solid of revolution. It is given by that right there. So this is something to remember. So I'll write this sort of in summary. When we spin f of x around the x-axis, from x equals a to x equal b, the volume of the solid is that formula. V equals, now I'm going to modify the formula just very slightly. That formula, as I wrote it at the top there, you will notice it has a pi on the inside. Pi is just a constant. You can always factor the pi out of the integral. So it's this. Pi integral a to b f of x squared dx. This is the volume of the solid. All right, this is a formula that is not, I guess, slightly harder to remember than that other area between the curves, but not so difficult. All right. Why exactly you will find yourself in the future, maybe if you look back at this formula when you're trying to review for the test or something, why exactly is it squared here and why is there a pi here? It's because the pi r squared in the formula for the volume of a cylinder, that's what causes this to be a square and this to be a pi. Although once you, I would say it's not worth even thinking about that really. You just remember the formula. That's where the pi comes from and the squared comes from, but you don't really have to think about the geometry anymore once you know the formula. All right, I was going to do a quick example, but the time is up. So we will, write that formula down. We'll start off from there and do some examples next time. All right, I hope you all have a good weekend. So get